I hope you all are doing well. Today we are going to discuss about what is semiconductor diode. A semiconductor diode is a two-terminal PN junction diode that conducts current only in one direction. PN junction diode is a two-terminal electronic component that has low resistance to the flow of current in one direction, and there will be high resistance in another direction. Okay. In this unbiased PN junction diode, you can see P-type material is connected to N-type material. Here, the one half of a silicon or germanium is doped with a pentavalent impurity and another half of a silicon or germanium is doped with a trivalent impurity. Then PN junction is formed. Here you can see in P-type material, empty holes are majority charge carrier and electrons are minority charge carrier. In case of N-type material, free electron are majority charge carrier and holes are minority charge carrier. Because of the electron and holes attraction, electron moves, so there is a recombination of electron and hole pair. So energy will loss due to this recombination process. As a result of electron recombination, the electron in N region are neutralized by the holes. Hence, ionized donor atom carrying positive charge are left behind. In this small region, you can see in this deflection region. Okay, so we have types of PN junction diode: LED, Zener diode, rectifier diode, tunnel diode, variable capacitor diode, photodiode, switching diode, and gun diode. Junction bias. The junction biasing of PN junction is the process of applying external voltage to a PN junction semiconductor diode. There are three biasing conditions for the PN junction diode, and this is based on the voltage applied. So zero bias means no external voltage is applied to PN junction diode. In our previous slide, we have seen unbiased PN junction diode. Here, no external voltage is applied means it is zero bias, forward bias. When P-type is connected to the positive terminal of battery and N-type is connected to negative terminal of battery, then the junction is said to be forward bias. When PN junction is forward bias, then there is formation of barrier potential between this P and N region. But that barrier potential is less, or we can say it is reduced when voltage is increased. So, when both the electric field added up, the resultant electric field has a magnitude lesser than the built-in electric field. This is the reason in less resistive and thinner deflection region. The deflection region's resistance becomes negligible. Then applied voltage is large. When we increase the voltage, then current will also increase. Means there is no resistance in PN junction diode, which is in forward bias. Means in forward bias PN junction diode, it has to carry more current. But in case of reverse bias, when P-type material connected with negative terminal of the battery, in this figure you can see this, P-type connected to negative terminal of the battery and N-type connected to positive terminal of the battery, then it is said to be reverse bias. In this case, built-in electric field and the applied electric field are in the same direction. When the two fields are added, then the resultant electric field is in the same direction. So the built-in electric field, the resultant electric field, we can see that barrier potential is increased. Means this deflection region is increased and this region become thicker. So no current will flow. As voltage increase, then the deflection region is also increases in case of reverse bias. Here you can see in forward bias, anode connected to positive cathode to negative, and in reverse bias, anode connected to negative and cathode to positive. Current flow. In forward bias, high current flow through the diode, but in case of reverse bias, very low current is flow. Deflection region. In forward bias, decrease in width, as we have seen in previous slide, because of that attraction of holes and electrons, there is a decrease in width. But in case of reverse bias, there is increase in width, totally opposite. In barrier potential, forward bias, barrier potential allowing charge carrier to recombine, but in reverse bias, barrier potential increase preventing charge carrier from recombining. Okay, and the behavior, conductive state when diode is on in forward bias, but in reverse bias, non-conductive state, diode is off. Voltage drop typically around 0.7 volt for silicon diode, and in reverse bias, minimal voltage drop. Close to zero bias. Application. Forward bias used in rectifier signal modulation and reverse bias used in voltage regulation protection circuits. Temperature effect. Forward bias increased current with temperature. Reverse bias leakage current increase with temperature. That's all about today's session. Thank you.